All right, so I'm Jared Elmore. I'd like to welcome you all to the first seminar of our fall FEC graduate seminar series. Our speaker today is Dr. Travis DeVault. Dr. DeVault is currently the Associate Director for Research and a Senior Research Scientist at the Savannah River Ecology Lab. He holds a graduate faculty appointment in the Warnell School of Forestry and Natural Resources at University of Georgia, where he advises his grad students. He obtained his bachelor's and master's degree at Indiana State University and his PhD at Purdue University. He was formerly the field station leader for the USDA SNWRC Ohio Field Station, and his research focuses on wildlife ecology behavior, specifically with respect to mitigating human-wildlife conflicts, mostly animal-vehicle collisions. I won't say the last line of what he told me to say, but it has something to do with the game on Saturday. He said, if you brought fruit, please hold it till the end, since he is a UGA associate.
All right, well, thanks, Dr. Elmore. I was assured that the Tiger fans are all very well behaved and would not vandalize my UGA vehicle. So I hope that's right. Anyway, yeah, so I'm at the Savannah River Ecology Lab. If any of you have never been there or have ever wanted to go there, let me know. It's a great place to visit. We've been there since 1952. The science of ecology was actually started by Gene Odom at the Savannah River Ecology Lab. So there's a lot of history there at the lab. It's a really neat place. We have 300 square miles at the Ecology Lab behind a high fence where we can do all kinds of cool landscape level manipulations and not have to worry about our equipment running away. So it's a great place to work. I'll be talking to you today about animal vehicle collisions, as Jared said. So we'll start with some background on animal vehicle collisions to get you all up to speed. Then I want to talk about two studies in particular, which give examples of the types of work we do in my lab, talk about some overall conclusions, and then tell you what I'm doing now. So when we think of animal vehicle collisions, this is often what comes to mind, and for good reason. Deer collisions are a huge problem throughout the country and in other parts of the world as well. But this is also a big problem. Smaller animals, often these go uncounted because they disappear really quickly on roads, and vehicle collisions with small animals can be a real conservation issue. So keep that in mind as we go through these slides. In terms of the numbers, this number is actually from Dr. Elmore's previous lab at Oklahoma State, but there are anywhere between 89 and 340 million bird automobile collisions per year in the United States. So at the upper end of that estimate, we think about nearly 1 million birds a day being killed in the United States just by cars. And to put that into context, we hear about wind turbines, it seems like all the time. Cars kill 850 times more birds than wind turbines. So this is a big issue, especially for T&E species. Now, there's also a problem with aircrafts, and there are recent years even more than that. 15,000 or so bird strikes reported, and I should say under voluntary reporting systems to the Federal Aviation Administration. And so this obviously is not near as big of a problem for conservation, but it is a big problem for people on planes. Most of these strikes don't cause problems, some of them cause big problems, as you probably all know. 1.25 million deer collisions per year. These numbers are from State Farm Insurance Company, 4 billion in damages every year. And this is not as well known, but there are over 1,000 aircraft strikes since 1990. Now, obviously, this is going to take off in mining, but this is a big problem, especially at smaller airports where they don't have good fences. And 85% of these collisions cause damage to the aircraft. There have been a lot of really bad accidents with deer and aircraft. Okay, so how do we go about working on this problem? Well, a real common way to address this is with hotspot analysis. So people count carcasses along roads, or there are accident reports put by the police, and people map these and then do a hotspot analysis. And this is really useful for finding out where the real problem areas are along roads. And this is how people can put in road-based mitigation methods like crossing structures or speed limit signs or whatever to try to reduce these strikes in the areas where they're most problematic. And you won't hear me disparage crossing structures. These things work, especially when combined with fencing to funnel animals toward these crossing structures, whether they're overpasses or underpasses for smaller animals. This is one of the very few mitigation methods we have that actually can demonstrably cut down on animal vehicle collisions. Problem is they're really expensive because they're usually put in after the roads are already built. And crossing locations of animals can be really unpredictable, so it's really impossible to put these things everywhere where they're needed. Aircraft strikes with birds especially, we've approached that in the past with a lot of habitat type work around airports. About 3/4 of bird strikes with aircraft happen at the airport, at these low altitudes where birds are most likely to be in the air. And so we've approached this in the past with mapping the habitat around the airport. For this slide, for example, we've done studies looking to see what types of grass candidates like to eat so we can plant other species at the airport. This is really the way this has been approached in the past, in addition to just dispersing animals away from the airport and trapping and relocating raptors, that type of thing. However, the problem with that approach, or the reason why that's incomplete, is because we've done a great job at the airport. This top slide there shows strikes in the airport environment, so that's less than 500 feet above ground level is what we usually consider out of the airport environment. These strikes have leveled off. Looks like I need to update this slide actually, but these strikes have leveled off. The trend's the same. We're doing a pretty good job at the airport. However, these are the strikes that happen outside of the airport environment. These have just kept climbing. And this is typically with birds like vultures that like to soar, or waterfowl during migration. These strikes are continually being a big problem. I have a project with the Navy right now looking at turkey vulture strikes in approach to departure corridors. This is getting bigger all the time. So, although we've made progress, a lot of progress in developing solutions to animal vehicle collisions, both on the roads and at airports, we still do have problems places where we can't put those crossing structures in outside the airport environment. And my argument is that we really need to know more about the fundamental causes of these collisions, and particularly at the level of animal decision making. To really learn how to address these strikes that are happening in these places where we just can't reach them right now for various reasons. So long time ago, my master's advisor was Steve Lima at Indiana State. He's just recently retired. He did a lot of anti-predator behavior work, and he and I worked together with a couple other co-authors. Gosh, it's been 9 years ago now, where we put together a review of everything we could find about how animals react to oncoming vehicles. And there's less than you think, even with like animals like deer that are collisions with all the time. But the way we approached this was that we looked at this hierarchy. And so there are all these different things that have to happen for an animal to be able to avoid a collision with an oncoming vehicle. It has to detect the object. Now, you wouldn't think that that's usually a problem to see a car or an aircraft coming along, but for some species it might be. But if it detects that object, it has to then assess it as a threat. Turns out that is the problem. I'll get into that in a minute. And then it has to initiate that evasion on time in order to avoid that vehicle. So problems at any of these steps can lead to collision. One of the early studies we did looking at what might go wrong, this study was led by Glenn Bernhardt. He was a technician of mine years ago. And I thought this was such a cool study. We asked airport biologists at JFK Airport, big airport in New York City, over a period of years to collect all the birds that they found along the runways and taxiways. So these were birds that we knew, dead birds that had been hit by aircraft. And then after we had 92 of these tallied up over a period of years, we did necropsies on all those birds to see where on the body of the bird it had been hit by that aircraft. And what we found was that the injury locations were most frequently on the posterior and ventral sides. They were not randomly distributed around the body, which would have indicated to us that the bird was blindsided and never saw the aircraft coming. They saw it and they tried to take an invasive maneuver, but they just couldn't do it in time. So this told us a lot. And again, I'm going to get into that more in just a minute. So, but this led us to ask, well, if birds are trying to get out of the way, they see the aircraft coming, they're trying to get out of the way, how they decide on when they actually make that that flight maneuver to get out of the way of the aircraft. So if we think about the history of birds, that's Archaeopteryx, right, on the left. Most people think that was the first bird, or very nearly the first bird. That fossil's from about 150 million years ago. So across the whole history of birds, 150 million years ago to today, the fastest things that birds have had to worry about have been predators, right? And most predators are traveling at 80 kilometers per hour or less. And there are a few exceptions to that, of course, falcons and whatnot. But for the most part, if you can handle something that's traveling at that speed, you're doing okay. Well, just in the past 100 years, we've completely thrown a wrench in that plan, right? So in the past 100 years, we've introduced these cars on the landscape, the Ford Model T in 1908, then aircraft, of course, which are traveling even faster than cars. So we really changed the landscape for birds in terms of oncoming threats. So modern vehicles are much faster than natural predators. So we asked, how do birds perceive and react to vehicles that are approaching at these really high speeds? And is it possible that birds might miscalculate the vehicle speed, and that's maybe what's causing some of these avoidance behaviors to be initiated too late? Okay, so here's, well, I wanted to point out, we've done a lot of these empirical studies over the years, driving trucks and model airplanes and drones at birds and at mammals to see how they react. Done some video playback work, I'm going to talk about that in a minute. But the study I want to talk about first here is this one we call Speed Kills, Ineffective Avian Escape Response to Oncoming Vehicles. In this study, we asked, how do bird responses to oncoming vehicles change across the speeds of those approaching vehicles? What strategies might birds use to decide when they take that avoidance response? And at what vehicle speeds do these avoidance responses become ineffective? Okay, so a couple definitions real quick. This is how we measure the perceived threat a bird has toward an oncoming predator or vehicle or whatever. So if a truck is approaching a bird, at some point in that approach, the bird will likely become alert to that oncoming threat. And with birds, that often means they orient their head toward the threat. Sometimes it's a head-up type posture, but usually they have some type of visual alert response. And we can measure that alert in terms of the distance. So the distance between the vehicle and the bird when it becomes alert. And we can also measure that in terms of time. And so when we talk about it in terms of time, it's the time that would elapse between when it becomes alert and when it would hit the bird. So it might be a few seconds, right? So we can measure that in meters or seconds. We also have the same thing with a flight behavior. We can measure that in terms of flight initiation distance, FID, or we can measure it in a metric called time to collision flight, which is the amount of time that would elapse when it takes off until that aircraft or that truck or whatever would hit that flight. Okay, and there are a couple different strategies then that a bird or deer or whatever might take in order to decide how to respond to that oncoming threat. The first one is probably the most intuitive, and it's what we might do if we're coming to the intersection and looking and trying to decide whether it's safe to cross the road, and that's a temporal strategy. So in that case, if a vehicle is moving really slowly, we can wait till it gets really close and it's still safe to pass. But if it's moving really fast, we have to cross the road or flee or whatever when it's further away. And the reason we call this a temporal margin of safety is because in this case, the bird or the deer or the animal would maintain a consistent time to collision. So if it allows more room when the vehicle is traveling fast, it can maintain that consistent time to collision. So let's say, for example, I want to maintain a margin of safety of 2 seconds, right? So under all these conditions, I can maintain that 2-second time to collision if I give it more room when it's moving fast. Now, the other way to approach that would be a spatial strategy. And in this case, the animal would say or think, I don't care how fast it's going, I'm going to completely disregard that. I'm going to take off when it's, say, 30 meters away, right? And so that might be easier to calculate and less prone to mistakes, but it might not be a good strategy in all cases because the time to collision will change drastically, right, across these different vehicle speeds. Okay, so in this study, we used video playback, and video playback has a long history in animal research. It's done with fish and birds and mammals and all kinds of things. We have a really good idea of the types of experiments that work for video playback and the types of experiments that don't. The advantage to us in this case was that we could make the vehicle look like it was traveling much safer or much faster than we could do safely in the field, right? We can speed up the video and make the vehicle look like it's coming really fast. And the other thing we can do with video playback is we can do direct approaches. So if you do this in the field, you have to do a near miss right beside the animal, or be prepared to brake really quickly. There's really some advantages to video playback. So in this case, we used 8 vehicle speeds, everything from 60 to 360 kilometers per hour. We had this bird's eye road level view. We played the videos in high definition at 60 frames per second. Most birds anyway, have a really good ability to detect flicker. So if these are fluorescent lights, I assume they are, they're probably actually flickering at 60 times a second. That would drive most birds crazy if they were in this room and watching that flicker, because they could actually see it. And 60 turns out is right on the edge of human detection. But most of us can't see the flicker, those birds can. So we played in 60 frames per second, which again tried to mitigate some of that. And we only use naive birds that hadn't ever seen these vehicle approaches before, and 3 birds per group. So this is our video chamber. It's just a box with TV, high definition TV on one side. That's kind of the view that the birds see. This is the picture that they would see coming at them. The reason there's a green screen on that is, I'm not going to talk about it in this study, but we had 2 different vehicle sizes, and that allowed us to control for what the front of the vehicle looked like by putting that screen on there. And then we could go in the other room and just watch what's happening right on video to these birds in the box. And here's kind of what this looks like. An example. So their alert behavior is right there. And there's the flight behavior. So this had never been done before with small birds and vehicles. We had no idea this was going to work. I remember Tom Siemens, who's a biologist I worked with to build this. We finally put this thing together and we finished it, put birds in the box, and we saw them react, and we got high fives on them. It's actually working. This is great. It fools them every time. It's amazing. They are totally fooled by this. And here's what we found. I'll jump to the chase here. That's flight initiation distance in the FID on the y-axis, vehicle speed on X. They did not change their flight initiation distance based on vehicle speed. They maintained a consistent flight initiation distance of about 28 meters. Turns out that's a really bad way to approach high-speed vehicles. And so they used this spatial strategy. These birds did not adjust any flight behaviors based on the speed of the vehicle. So you might be asking yourself, well, how reliable is it and realistic are these data you're getting from the video playback lab? Well, it turns out my colleague Brad Blackwell had done 2 previous studies approaching cowbirds and mourning doves in the field. And he was not interested in the same question that I'm telling you about here. This was about vehicle lighting and how birds reacted to different types of vehicle lighting. But it just turns out that in that first study he published in 2004, he was going really fast, 121 kilometers per hour for the controls without any special lights. And those are the FID numbers for the birds. So in this later study, just for experimental reasons, he approached it really slow, and they were almost exactly the same. So this told us that we had some evidence that what we were seeing in the video lab anyway was real. It was not just an artifact of video playback. Okay, we were also interested, as I mentioned before, not only in how they made these decisions based on vehicle speed, but at what vehicle speed did these responses become ineffective. And so we needed to know how long it took, once a bird took flight, how long does it take for that bird to clear the path of the vehicle safely to get out of the way? So we estimated that a bird would need to go about 3 meters from where it was sitting in order to get out of the way of the path of the vehicle. So we decided to figure out how fast a bird can fly 3 meters. So we put Tom at line and put the cowbirds here on the perch, and then we had some measurements there, and then he jumped out of the blind and scared him with a starter pistol. And And we did that several times and got some measurements. And it turns out it takes about 0.8 seconds pretty consistently for birds to travel that speed. So we knew we needed a cushion, if you will, of 0.8 seconds when it first takes off to get out of the way of the oncoming vehicle. Well, these are the same data I showed you before, but it's just expressed in terms of time to collision. It's this temporal measurement of their responses rather than distance. So time to collision, flight, and then this is the vehicle speed. So at 60, 90, and 120 kilometers per hour, they took off with enough time to avoid that vehicle, because this is the 0.8 seconds, right, that they needed to get out of the way. But once you got past 120 kilometers per hour, they would have been struck. That would have been a real vehicle. So this is pretty remarkable if you think about it. So these birds, there's a vehicle coming on a direct collision course. It can see it coming. There's no problems with protection. It's not distracted by anything, but it cannot get out of the way of a vehicle going past a certain threshold speed, just because of its behavior. So our primary findings here, cowbirds usually responded quickly enough to avoid collisions during low-speed approaches, but they were overwhelmed by these high-speed approaches. They did not adjust their escape responses for differences in vehicle speed, but instead used the spatial rule. And at high vehicle speed, this lack of adjustment left them little time for avoidance. And this is a little bit of speculation, but this is probably a remnant of anti-predator behavior. So what birds, again, mostly had to worry about throughout the history of predators, right? Predators have a very small range of speeds that they approach at. You know, it's fixed by the flight dynamics and the types of animals that they are. So this spatial rule probably worked great for avoiding predators for all these years. But now we're throwing vehicles at them, doesn't work well at all. So some caveats, of course. Not all collisions are caused by miscalculations involving vehicle speed. There's problems with detections, distractions, all that, many collisions are not head-on. But if birds innately respond in the way that we've shown, very fast vehicles are an especially serious problem. And vehicle speed can be a major contributor to collisions. And we've not just seen this with cowbirds, we've had similar evidence from a variety of species that I can't tell you about. But it looks like this might be a general rule, not just in birds, but also in some mammals. Deer, the only ones have been able to test so far, but we're seeing the same things in deer. Okay, and I was really kind of pleased by Science Magazine put out a short commentary after we published that study, and white birds crash into planes, and so I thought that was pretty cool to see. All right, so we know that this is a problem. High-speed vehicles are everywhere, though, all across the developed world. I mean, birds, deer, everything. They're seeing planes and boats, cars, trains. You know, they're all traveling really fast. So we began to ask, you know, after that study, well, how can birds cope with all these high-speed vehicles? Is it possible they can use experience with passing vehicles to decide on that flight response? So again, across the developed world, birds observe many vehicles each day. Now, here's the key, though. They don't pursue the birds, right? Instead, they travel along these predictable paths, roads or railroad tracks or flight paths. And so if birds are watching, you know, these passing vehicles all day long, how might they use experience with that to alter their flight response? So we had three hypotheses here on the roles of experience. The first is we thought, well, birds might see these passing vehicles and know that they're not on a collision course with them, and so they think, well, that doesn't have anything to do with me, I'll just ignore it. So in that case, it would have little effect on their flight initiation distance. But it's also possible birds might see those vehicles passing and go, man, those are really fast. If ever anyone chases me and comes right at me, I'm gonna have to give it a little more space, right, before I take off. And so in that case, we see an increased flight initiation distance. But it's also possible that birds might become habituated to that, right? They might be seeing all these passing vehicles and thinking, man, those things never chase me, they're not a problem, I should just ignore them. And in that case, it would decrease that flight initiation distance. So in order to do this study, we use rock pigeons, just your common city pigeon. But we needed birds that had never before seen a vehicle because we just wanted to expose them to a certain level of experience with vehicles. So we bought birds that were raised in a barn that never before seen a vehicle before we got them. And so we trained them with 32 vehicle approaches over 4 weeks. We exposed them to a certain level of vehicle approach, but we separated them into 3 groups. The first group was trained at vehicles approaching at 120 kilometers per hour, the second group at 60, and the third group was a control. It went out to the same place the other groups were, but it was in a covered cage, so it never actually saw the vehicles approach. They just could hear them, just like the other birds. Okay, so here's our field set up. Again, we're driving a truck down the road, the cages with the birds. Here are the 2 training groups and the control group, and we just drove by, again, 32 times over 4 weeks. So we went and got the pigeons out of the aviary, put them on a truck, covered the truck so we couldn't see any vehicles on the way, put them out by the side of the truck. And this is what this approach looked like. This was done at a NASA base, closed the traffic, closed roads, and do all that kind of cool stuff. So for measuring flight initiation distance, however, we went back to the video playback lab because we wanted, again, to measure their response to directly approaching vehicles, and we can't do that in the field. So even though the training and the measurement of their response was different, one was in the field and one was in the video lab, I'll stress that the only difference between these groups was the training that they got. So any change that we saw in their response in the video lab had to be due to that treatment that we gave them. So again, it allowed high-speed approaches and head-on approaches. We took 30 birds from each group, tested them one at a time, either 120 or 240 kilometers per hour, recorded the behavior, and quantified flight initiation distance. So here's what the birds saw. This was the video they saw in the lab. And this is how they reacted. You see that alert. You can go back and slow down those videos and measure it really precisely. So during video playback, we saw avoidance responses in almost all of them, 83 or 90, there were 7 of the birds that didn't do anything. And we found that, interestingly enough, the control group, so again, these are birds that never saw the vehicle during training. They've never seen a vehicle in life for that video lab. They actually had better or longer flight initiation distances than the ones that we exposed to the vehicle approaches. So the naive control group had a longer FID than the 2 training groups. We didn't see any difference in the 2 speeds of the training groups there. And the virtual vehicle approach speed and interaction were not significant. So our primary finding was that inexperienced birds had longer flight initiation distances in response to a direct vehicle approach than the experienced birds had. So experienced birds evidently learned that the vehicles pose no threat. We can't officially say this is habituation because really to study habituation, you have to have the same measurement time after time after time. We only had the one measurement, but it sure looks like that's what's going on. So the conclusions here: experience does not mitigate adverse effects of vehicle speed. Habituation could contribute to any vehicle collisions. And one of the reasons we did this study was because there were a lot of airport biologists around the country that, normally they would trap raptors. They find at the airport and move them away from the airport. But there were a certain segment of biologists that would say, no, we need to leave those raptors that are living at the airport there because they're experienced, they know how to deal with vehicle traffic, with aircraft. And if we move them, there's just going to be inexperienced birds come and take their place, and they're more likely to get hit. So we didn't definitively solve that problem with this study, but what we did show was that it's very possible that actually the experienced birds might be less likely to get out of the way of the aircraft. And just about 2 weeks ago, I have a PhD student who's studying bird movements around airports and has a GPS trackers on red-tailed hawks right now. And one of her experienced birds just got whacked by an aircraft at Savannah just 2 weeks ago, and it had been there for a while. So, I mean, definitely these experienced birds very well might be becoming habituated. Okay, so what have we learned from these 2 studies? Birds are usually not blindsided by vehicles. They try to initiate avoidance, but they often do so too late because they use this spatial. Can they compensate by using experience? Probably not. Habituation could be a problem. Now, are there other ways we can elicit an earlier flight response or increase that FID? We've been messing around with vehicle lighting for over a decade, trying to put lights on vehicles that are especially salient to the species that we're most worried about. But that work is ongoing. So I just wanted to show you a couple slides And I should say this work is in collaboration with my old USDA colleagues, especially Brad Blackwell, and then also Stephen Fernandez, who's a professor at Purdue University, who we've been working with on this for years. And so in this study, we took 5 LED lights, and these are colors of lights that we knew cowbirds could see really, really well. So there wasn't a problem with seeing the lights. And we put them in a Y maze. And so we put one of these lights on one side, the other side didn't have anything, let the bird go and see if it avoids the light or is attracted to it. And so here's the Y maze, and we put the light on there. Here's what that looks like. Oops. So you let the bird go, it's trying to get away from you, and it chooses a side, right? And then you do that a number of times, and you can get some statistics. And what we found was that, so on this graph, this is no preference along the middle here for any of these lights. And this is going toward the light, and this is going away from the light. We found out that blue lights at 470 nanometers and just barely red lights, they tended to avoid. So that's good news. Now we have no idea why they would avoid some colors and not other colors. But at least we know now that there are certain lights that make some sense. My current research priorities, again, I'm still trying to understand these animal behavioral and sensory ecology and with respect to animal vehicle collisions. Now, since I moved to UGA 2019, I'm still doing some bird strike work with aircraft, but I've started doing a lot more road ecology stuff since 2019 and working a lot on deer and vehicle lighting. Also using movement behaviors. I just mentioned at airports and build bird strike risk models. And I'm very interested in this idea of vehicle speed on highways and posted speed limits and whether that makes a difference. A few more examples here. So, I showed you the hotspot analysis and the crossing structures. So we've been working on vehicle-based systems. So the nice thing about vehicle-based mitigation methods is they're always in the right place, right? They're on the vehicle itself. So we don't have to worry about trying to choose the right spot for mitigation methods. So a vehicle-based mitigation system, especially if we're effective for deer, would be a real advancement in reducing animal vehicle collisions. So the only thing we have available right now that you can go and buy to put on your car are these deer whistles. Has anyone, familiar with this, ever seen this? So these are these little things that they're just, 15, 20 bucks, and you stick them to the front bumper, and the wind's supposed to go through them and create a sound that the deer don't like. It gets the deer out of the way. So I was looking this up on Amazon, and there are hundreds of these products now. The patent must have run out. They're selling like hotcakes, and they all get really good reviews. Look at these reviews. This guy cracked me up. So he installed the deer whistle. As I get close to the deer, quickly runs away. And so now I know it works, right? I think there's a correlation and causation problem there. Interestingly enough, there have been 2 studies done. This second one by colleagues at the University of Georgia, they have no effect on deer behavior whatsoever. They do not work at all. But hey, someone's making money on it. So. But anyway, we have nothing right now in terms of a vehicle-based mitigation. So I've been working on this idea of changing the lighting system on vehicles. And most deer collisions are at night, a pretty strong majority are at night. And so I had this idea that maybe it's the headlights are the problem. So deer have very dark adapted eyes. And it's quite possible that these headlights are just not well suited to deer vision at night because they have these dark adapted eyes, you have these 2 small pinpricks of intense light. And maybe these headlights provide a smaller looming image, right, than it would see during the daytime with vehicles. And it also might be that these 2 little pinpricks of light, the deer's not associating with danger. Maybe it doesn't realize there's a very heavy, fast-moving vehicle behind those lights that are coming at it. And that might be causing this freezing behavior. You've all heard of deer freezing in the headlights, right? Well, maybe it's trying to just figure out what in the world's going on with these 2 lights coming at it. So if we could have a mitigation method that reduced that, we'd be in business. So I had this idea about putting a light on the front of the vehicle and turning it around. So what I did here was I put a light bar on the front of the vehicle and shined it back at the grill of the vehicle. And so the idea here was to increase that frontal illumination of the vehicle and make a bigger looming image that the deer could see coming at it. Maybe it provides a more familiar looming cue and you have fewer interactions. So here's a little video of what it looks like. There's what it looks like when it's on. compared to what it looks like when it's off. It's a pretty big difference. For this study, I just used an LED regular light bar you can buy on Tractor Supply or whatever. Nothing special about the wavelength. But long story short, since I don't have much time, it seems to work. So this is, so we call the dangerous interaction is when the FID of the deer in response to the vehicle is 50 meters or less, because generally with braking time, you can't brake in time to avoid a deer if you see it at less than 50 meters. And so here's the FID is 0, these white bars at the bottom, that means the deer froze. It never did anything when we approached it. And these lighter gray bars are, it did take off, but it was less than 50 meters. So those together are dangerous interactions. The not dangerous interactions are FIDs of more than 50 meters. We cut this down big time. 35% dangerous interactions to 10 by using that LED light bar. And we think what's going on is it almost completely reduced the freezing behavior. We only had one deer that froze in response to the headlights when we had that light bar on. Now I have a student right now, a PhD student, Carson Pakula, who's still looking at that idea of the LED light bar, but he's also looking at LED versus halogen lights, and whether that has an effect on deer behavior, and then bright and dim lights to see what the response is there. And the reason we're looking at these LED versus halogens is because the wavelength or the color coming from those lights are very, very different. So these are the peak visual sensitivities of deer, these vertical lines, the short wavelength cone, the rod, the long wavelength cone. They match up pretty well with LED headlights. So it could be that we're actually just bombing these deer with really bright lights that really hit those photoreceptors, the LEDs. And comparing that to halogen, the old style lights, how do deer react to that differently? And by the way, 85% of cars produced now are going to LEDs, and that just happened really, really recently. So he set up a study where we have a factorial design in 3 different treatments: bright versus dim headlights, LED versus halogens, no light bar versus light bar. And we set up this captive study at the UGA deer facility. So here's this factorial design. There's 8 different combinations of treatments. And we let the deer out of the barn at night. So the deer are in this barn, we let them out, and then we have this golf cart that we modified with different headlights and light bar, and it looks crazy. But we've got this crazy golf cart that we're driving toward deer. And then when they come out, they're trying to get away from the people in the barn. We come out in the other direction. The golf cart with one of these different treatments. This is what that looks like. So there goes the deer. He's running away from the person in the barn, and then you start the approach. And then we can measure at what point that deer responds to that oncoming vehicle based on the treatments that it has. That was a big one. So we just finished it, and we're analyzing the data right now. So I don't have anything exciting to say. We should be getting that out for too long. And then he's also doing a similar study in the field there at the Savannah River site. And if any of you are going to the Wildlife Society meeting coming up, he's going to be talking about some of this. But we have a nice clear system on the vehicle, and we can use different headlight combinations and approach deer at night and see how they react to all these different combinations. So that's what's going on right now. That's what I got. So thank you. Questions? Yes.
Did you put a light bar on your personal phone?
I have not yet, but I certainly would. So we're one of the things we found out when we started the field work at the Savannah River site is there appears to be an interaction between the type of headlight, whether it's halogen or LED, and the use of the light bar. So we're trying to tease that out right now to see under what circumstances it works best. But we actually do have a patent on it, though. So I was still at USDA when I did that study, and it's right before I published their what do they call it? The people that deal with patents. Anyway, I got a phone call like, "Don't publish this yet." He said we need to submit this for a patent, so we did, and it went right through. So I'm hopeful that will, if this turns out to be as promising as I think, I'm hopeful that will lead to quick adoption of it and getting it out. Yeah. Yes.
Me? Okay.
Yeah.
So I'm curious, with the bird studies, especially the one where they may or may not be like learning how to deal with cars or vehicles. Have you done any studies on other species? There's like the connotation that maybe pigeons aren't the smartest, but maybe with like crows or something. Do you think different species might be able to learn?
Yeah, that's the only study I know of that's been done in that respect. So that's one study, and there's a ton going on there. There are some data on crows that show that they're able to, the crows are they're actually underrepresented in the FAA's bird strike record. I think that there's something going on there with intellectual capacity. But yeah, if you notice crows on the road, when most birds, if they're on the road like vultures, they take off, right? If you're going slow enough, they take off. Crows just move the other way. They've gotten really good at kind of dealing with that. So I absolutely think there's something there with brain size. We just haven't been able to tease it out yet.
Cool.
Yeah.
Do you have any thoughts on, some birds and other species you see outside of the visible spectrum? We see any thoughts on like using special lights that we may not be able to see that they can see?
Yeah, I want to hear that. So the question was about using, and UV lights, right? So some birds, not all birds, some birds can see the ultraviolet pretty well. There have been a ton of, well, let me back that up. You can't put whatever light you want on an aircraft, right? There are a ton of regulations about the types of colors of lights you can put on an aircraft. The pulsing frequency, you don't want to give pilots vertigo, right? And there is a real chance of that. So there are only certain types of lights the FAA will allow on aircraft, and it's very restrictive. So to get around that, there have been people for years that have been promoting UV lights for bird strike avoidance. And the idea there is people can't see UV, birds can. So if we put UV lights on, it solves the problem, right? Well, in theory, that makes a lot of sense, but one thing we found with our research is just because a bird or a deer or whatever can see a light, it does not mean it will have a repellent effect. Right? It's not an automatic, getting them out of the way. And in the one study I showed you and a couple others, we found that UV lights seem to not have any effect for the species we've tested as far as a deterrent effect. We don't know why, but I will say that UV cues are used by some birds for feeding. So maybe that's not the best key to use for, trying to get them. And also, the other point there is some birds can't see UV. I know of someone who spent a lot, matter of fact, I got a call of someone who spent a lot of money trying to develop UV deterrent to wind turbines and specifically for golden eagles. And this guy's business sunk a lot of money into that. And there was a study that came out not long after that showed they can't see UV. So, there's that problem too. You gotta know that biology. What else? Yes.
Yeah, so other than the deer whistles, we talked a lot about visual sensing, but you mentioned sensory biology in general. Any other like sound, air, physical sense that
so
videos might miss?
So much of my previous work has been involved with aircraft strikes primarily. So in that case, we're mostly considered with birds. Birds are very visual animals, and planes are going so fast anyway that sound might not be the best cue there. So we have concentrated in my lab mostly on visual cues. I think there is possibility for sound cues, especially in road ecology. We just haven't done a whole lot of it. But I think there could be some progress made. I tell you, especially if we could figure out something with pigs. I mean, my student Carson Akula has been doing a lot of work on pig strikes around the small rivers, and we cannot get those things out of the way. They just don't care. They sit there. People don't see them. People are terrible at seeing. We did a study looking to see how well people see animals along the roads. They see the deer much quicker than they see pigs. Pigs don't have eye shine, they're loaded around the dark, you can't see it. So anything we can do in the future to work on the growing problem of pig vehicle collisions, and maybe sounds like that, I don't know. Yes.
I know you said that experienced cowbirds were worse at responding to oncoming vehicles. But do you think that if you had a study where like you showed them vehicles hitting like a bird dummy, that they would actually be scared?
I don't know. I think that's, I think it would make an interesting study, in all honesty, to see if that kind of thing helped. I will say that we did a study years ago where so there's this idea that you can put out effigies, right, of vultures, especially if you hang a dead bird that, other birds, and they work very well for some species. They're afraid of it, won't go near. So we were wondering about cowbirds and whether they, and the reason we use cowbirds, by the way, for a lot of our experiments is one, because we know a lot about their vision. There's been a lot of visual work done on cowbirds. And also they flock in huge numbers and we can catch a zillion of them. And they do really well in captivity. So they've been a great model species for us. But we did a study where we actually shot cowbirds in the presence of other cowbirds to see if that kept them away from a feeding trough when they were fast. They couldn't care less. They would literally walk over corpses to get to the food and not care. So it's a really good question, but what we've seen so far is that for some species anyway, it doesn't seem to make a difference.
That's weird.
Thank you so much. I knew it.
Yeah.